In 1861, James Clerk Maxwell, a Scottish scientist, comes up with this theory to explain electromagnetic radiation, of which visible light is a type. He says that electromagnetic radiation, or sometimes we just call it EMR, is generated by or is caused by accelerating electric charges. Now be careful here. EMR is not caused by electric charges. EMR is not caused by moving electric charges. EMR is caused by accelerating electric charges. Electric charges in general, just stationary electric charges, will generate a gravitational field. They'll generate an electric field. They will not generate a magnetic field. Charged particles that are moving at a constant speed will generate a gravitational field, an electric field, and a magnetic field. Charges that are moving with an acceleration will generate a gravitational field, an electric field, a magnetic field, and EMR. Accelerating charges, according to Maxwell's theory, generate electromagnetic radiation. Why? Why? Well, because accelerating charged particles are necessary to produce a changing field. Right? A moving charged particle generates a magnetic field and an electric field, but the magnetic field and the electric field aren't changing, and the changing nature of them is important. Why? Well, because changing magnetic fields generate changing electric fields, and changing electric fields generate changing magnetic fields. If you were here on Thursday before the break, remember the little thing that I did? This, right? We had an accelerating charged particle that generates this changing electric field and this changing magnetic field. This electric and magnetic field generates this magnetic and electric field, which generates this electric and magnetic field, which generates this magnetic and electric field, and so on and so on and so on. If we have just a moving charge, sure, we get an electric field and we get a magnetic field, but nothing else. You can't get this continuous nature of it, this movement, this propagation of this EM wave, unless we have a changing electric and a changing magnetic field. In order to get those changing electric and magnetic fields, you need the accelerating charged particle. So, accelerating charged particles generate changing fields, and changing fields kind of self-propagate. Changing fields generate changing fields, and those changing fields generate more changing fields, and that's what EMR is, electromagnetic radiation is. So, you need accelerating charged particles to generate changing electric and changing magnetic fields, or to generate EMR. Now, which way do these waves travel? These electric fields and magnetic fields, they're perpendicular to each other, but they will travel perpendicular to both of those waves as well. So if this is, let's say that this is electric field right here, number 1. That's on our y-axis. We've got a magnetic field, number 1, right here. Okay, that's on our z-axis. We would say that electric field number 1 would generate magnetic field number 2. And magnetic field number 1 would generate electric field number 2. And so on and so on and so on. Perpendicular to each other and perpendicular to the direction of propagation. If there's 3 words that you can remember to summarize what we just said, those 3 words would be accelerating, because it's accelerating charged particles that are necessary to cause all of this. The second word would be changing, because accelerating charged particles generate changing electric and changing magnetic fields. And the third word, anybody remember the third word? We saw this in the last unit quite a bit. We'll see it in this unit quite a bit as well. Starts with a P, perpendicular. Accelerating charged particles generate changing electric and changing magnetic fields that are perpendicular to each other and perpendicular to the direction of propagation of the wave. Remember those 3 words? You're probably going to be able to answer any question that we throw at you with that relates to this stuff that we just talked about. Now, Maxwell said that EMR consists of these changing electric and changing magnetic fields that produce a wave. And electromagnetic radiation is an electromagnetic wave, a sinusoidal wave that consists of these 2 fields, double perpendicular to both of them. One thing that supports the wave nature or supports Maxwell's theory of EMR are these, or I should say four things that support Maxwell's theory of EMR are these four properties of waves that are exhibited by EMR. Diffraction is one. If you remember physics 20, diffraction is the spreading out of a wave. Here's an opening. Here's a wave that goes through that opening. As it goes through that opening, it spreads out like this. That's called diffraction. And diffraction is a property of waves. It happens in waves, but it also happens in EMR. So therefore, well, according to this at least, Maxwell must be right. EMR must be a wave. Interference. If you remember interference from physics 20, if we had let's say a crest this way, like this, and another crest like this, if we add these together or combine them, then we would get a wave that looks like this. It's called constructive interference. Two big waves, get a bigger wave. You get a big wave on one side, a big wave on the other side, they cancel each other out, produce destructive interference. Interference is a property of waves, but it's exhibited by EMR. So therefore, at least according to this, Maxwell's theory is right. EMR is a wave. Refraction was the bending of a wave. And you had a wave coming towards a boundary like this, counters the boundary, and it changed direction. Changed direction because the speed changed. We'll talk about that more in another week or so. But it bent, changed direction. That's a property of waves, but EMR undergoes refraction. The direction changes and it goes from one medium to another. You know this, right? You stick a pencil in a cup of water, it looks like the pencil's bent, right? It looks like the pencil's bent because the light changed direction when it transferred from the water to the air. It's refraction. It's a property of waves. It's exhibited by EMR, therefore EMR must be a wave. Finally, polarization. This is the new one. Probably never even heard of that before. Lots of you at least never heard of that before Thursday. Polarization is the filtering out of certain components of a wave. Put a wave through a polarizing filter, it takes some of those components of the wave and makes them disappear. It filters them out. That's a property of waves, but it's exhibited by EMR. So therefore, once again, at least according to that, EMR must be a wave. These are four properties of waves that are exhibited by EMR that lends credence to Maxwell's theory. What I want to talk about now for the next couple minutes is a little experiment that was done by Hertz, a German scientist. Recognize his name? Hertz? Frequency, right? Remember physics 20, the frequency of a wave, the frequency of rotation of something in a circle is in Hertz. Same guy. You do work with EMR and you get a unit named after you for frequency. Hertz did an experiment called the Spark Gap Apparatus where he experimentally verified Maxwell's theory. Okay, he experimentally observed EMR and from that drew a conclusion that Maxwell's theory was correct. Here's how that experiment went. And this is new. We talked about everything we've done up until this point, we reviewed from last Thursday. Okay, this is new. Hertz's experiment looked something like this. He had an AC power supply. An AC power supply, by the way, is just the electric current that's going back and forth, back and forth. That is as opposed to a DC power supply, which would have a symbol like this, right? Just a regular battery. DC is direct current. Electric current is flowing in one direction only. AC, it's alternating current. It's flowing in one direction, then the other direction, and then the first direction, and then the other direction, and so on and so on. So he has an AC power supply with a really, really high potential difference. And somewhere over here, he's got a little bit of a gap. If we have a high enough potential difference, then electrons can jump across that gap. Just like if we have a high enough potential difference between a cloud and the ground, we get lightning. Electrons jump across the gap between the cloud and the ground, forms lightning. So if we have a small potential difference, nothing's going to happen here. If we have a big potential difference, then electrons can jump across the gap. Now, as they jump across the gap, they accelerate. There's no groundbreaking science to this. If the electrons are gathering on one side of the gap, and then all of a sudden they jump across the gap, well, then they must have accelerated in that process. Hertz reasoned that if he could detect EMR here, if he could detect the presence of EMR, then Maxwell's theory must be correct. Because remember what Maxwell's theory said. Accelerating charges generate EMR. If he can detect EMR, then that EMR must be due to the accelerating charge particle, and therefore Maxwell's theory that accelerating charges generate EMR must be correct. So how does he go about trying to detect this? Well, he introduces an antenna. An antenna is just a conductor. It's just a wire, a conductor. How does it detect the presence or absence of EMR? Well, listen carefully. Maxwell said EMR consists of changing electric and changing magnetic fields. If you have a changing electric and a changing magnetic field, and this antenna is exposed to that, then the antenna will have induced in it an electric current. A changing magnetic field will generate an electric current in the antenna. So Hertz reasons if he can detect an electric current in the antenna, then there must have been a changing electric and a changing magnetic field, which is what Maxwell said EMR was. And that must have been caused by the accelerating charge that we have right here. So he flips on the switch, guess what happens? He measures an electric current. Maxwell's theory must be correct. The only thing they could explain the electric current that was produced in the antenna was a changing electric and changing magnetic field, which came from an accelerating charge, which is exactly what Maxwell said would happen. When you have an accelerating charge, you'll generate a changing electric and magnetic field, which is EMR. By the way, the type of EMR that he used, it wasn't that he necessarily tried to pick a specific type of EMR, just the way that he set up his experiment happened to be radio waves. In fact, not only do we give Hertz credit for experimentally verifying Maxwell's theory of EMR, we give him credit for the discovery of radio waves. Radio waves existed before, but nobody else had really used radio waves to do anything. Nobody else had ever detected radio waves experimentally, so he gets credit for both. Experimentally verifying Maxwell's theory and the discovery of radio waves.